Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. Today we are on the lecture 2 of chemical kinetics. In the previous class we have discussed a few important things which will become the basis of this particular chapter. We actually discussed about what is rate, what are the two different types of rates. We talked about the instantaneous rate, we talked about the average rate, and then we also studied the rate law. And also, my dear students, we studied a little bit about order and molecularity. Today we will be just continuing that particular part and we'll move forward to our next session. I hope all of you are excited, so let's start the amazing session. What are we going to study today? We will be studying about order and molecularities. Okay, not this. And then, my dear students, we'll be talking about the zeroth order reaction. Okay, so this is the main part which we will be covering today. I hope all of you are excited. I am super excited. So let's start the session. So now, my dear students, in the last lecture we were actually discussing about the one step reaction and the multi-step reactions. The one step reactions were actually the reactions which take place in one step. Let's say you have a reactant and it goes into product, and this is a one step reaction where a reactant has converted into a product. And we also call this particular type of reaction as unitary elementary reaction as well, right? Yes. Then we talked about the multi-step reaction. In multi-step reaction, we actually see a single reaction. Example, we say that A made D product, but actually this reaction takes place in small steps. And what are those steps? First, let's say A converts to 2B, and your 2B will convert into C, and then, my dear students, C will get converted into D. So basically your A has finally got converted into your D product, but actually it happened in n number of steps, right? Yes. So this is a multi-step reaction. Also, we call it a complex reaction. So today we will be discussing, we'll actually combine these two topics which we have studied, the different types of reactions, multi-step and single step, and the order and molecularity. We also discussed that for a single step reaction we can define molecularity, for a single step reaction we can define molecularity, but if we have a complex reaction we cannot define molecularity. We'll be studying today why is this so. I hope all of you are excited. So let's start. Just let me see whether my voice is being recorded or not. Yes, it is. So now we can start the session. Okay. So, my dear students, for this, I just want to make you understand through a graph a very important thing. Whenever, let's first plot a graph. Okay. So imagine we have an energy profile, something like this. Here you have energy, my dear students, and what happens in chemistry is that you all know that in chemistry, the more the stable a species is, the lesser will be its energy. If any species has a very high amount of energy, definitely it is not stable, right? It is in its excited state and it actually wants to get stable. And how a species can be stable? It will actually give out its energy and will be stable, right? Yes. So basically anything which has very high energy is not stable. Everybody just wants to give out their energy and be in their stable state, right? Yes. So this is the basic concept which we will be discussing. So now imagine, my dear students, if we say a reaction is spontaneous, let's take an example of a spontaneous reaction. Let's say R is getting converted into BP product, and this is a spontaneous reaction. So what does this mean? What does this spontaneous reaction mean, my dear students? This means that your reactant was in some high energy state. Your reactant had high energy and your product has lesser energy, and that is the reason lesser energy, and that is the reason reactant actually got converted into product. Okay, if a reaction is spontaneous, then definitely the energy of product is comparatively less than the reactant's energy. And now let's try to understand with a graph. Let's say you have an energy profile here and you will have reactants here, and this is the amount of energy your reactants have. Okay, so what happens is this, these react, and your the energy of your products is somewhere here. Okay, so now your reactant will definitely want to get converted into products because the energy of reactants is more and the energy of products is less, right? So reactant wants to get converted into product. Okay, so this is a spontaneous reaction and it actually takes place something like this. Okay, let's say the reaction is, when we say reactant to product, let's say you have AA plus BB, you have two reactants and it is getting converted into AB. Okay, so now what actually will happen, my dear students, is your reactant will get converted into products. Definitely the energy of reactant is more as compared to the products, that is also right. But what you see is first reactant goes till here and then it comes to the product, and this particular state is your transition state. What is TS? It's transition state. Okay, this is your transition state. So now we need to understand a little bit about this transition state. Okay, I just want to make you understand, till now I am talking about a single step reaction because reactant is getting converted into product. So if you want to write it, then just write it, don't get confused. We are talking about a single step reaction. Okay, ma'am is talking about a single step reaction. Okay, so now what can I say, that your reactant is getting converted into product and you have a transition state. What actually is a transition state? If you talk about this single step reaction, AA and BB are your reactants, they actually do react together and form AB. This means that in this process, while forming AB, what will happen, there will be a state where AA bonds will be broken, your BB bonds will also get broken, and a new bond will be formed between AB. And all this process takes place simultaneously. At the same time your AA and BB are breaking their bonds, at the same time AB bonds are getting formed, right? Yes, and this is your actual transition state. This is what is known as transition state. And after this, my dear students, your final product, that is AB, is formed, and that is your product. Okay, so what I want to tell you is that this state where the bonds are simultaneously being broken and formed is actually known as the transition state. And this transition state has a very high energy, and since it has very high energy, it is highly unstable. It is highly unstable. Okay, so this is your transition state where actually your reactants bonds are getting broken and your reactants actually are combining to form a new product and their bonds are being formed. And this state is known as a transition state, and every reaction has a transition state, and the transition state is the state where it has the maximum energy, and that is the reason it is the most unstable. And once the products are formed, you move to the lowest energy and your products is the most stable state. Okay, so this is how the process takes place. I hope you are clear with the concept of the stationary of the transition state, right? Yes. So since it is a single step and a reactant is getting converted into a product, this means that, ma'am, since it is a single step reaction, it will have only one transition state. So the important thing to note here is that a single elementary reaction has only one transition state. Okay, your elementary step will have, your elementary reaction will have only one transition state. Okay, and when you talk about a single step reaction where you only have one transition state, you can say that it is a elementary reaction. This is actually the code. You can just see that if it has one transition state, definitely it is a elementary reaction. Okay, yes, the next thing which you need to understand is, my dear students, that for the elementary reaction, since the same reactant is getting converted into products, so we can say that the molecularity of this will be given is equal to 1. Since we are talking about one reactant, if it had two reactants, then we would say molecularity is 2. That means that you can define molecularity for a elementary reaction. So the other point you need to write is molecularity is equal to the number of reactants in elementary reaction. Okay, and the last thing which you need to understand is, for a elementary reactions, you can define the molecularity, and that molecularity will be equal to the number of reactants. Okay, and the most important thing to note here is that for elementary reaction, my dear students, only and only for elementary reaction, your order is always equal to the molecularity. So the third is, for elementary reaction, order is equal to molecularity. Okay, so only and only for elementary reaction you can say that the order will be equal to molecularity. Okay, yes, I hope you're clear with this. These are the things which you need to understand about a elementary reaction, about its molecularity, about its order. Okay, so please write it and then we'll move forward. I hope you've written it. Now let's move forward. Now, my dear students, let's talk about a multi-step reaction, right? Now we will draw a plot for multi-step reaction. For a multi-step reaction, again, your energy profile will be something like this. Let's say here you have energy. Okay, now let me write a multi-step reaction for you. Let's write that you are getting A to D. Your A is getting converted into B, and then your, let's say it is getting converted into 2B, and then your 2B is getting converted into C, and C is getting converted into D. And finally, if you see, then your A is actually getting converted into D. Okay, so I can say that this is the mechanism or the steps that are actually involved in the formation of a product from the respective reactant. Okay, yes, so this means that your multi-step reaction A to D actually involves 3 different steps, and then you get your final reaction. Okay, so my dear students, in multi-step reactions, the point to note is that order is never equal to the molecularity. First thing, order is actually calculated here experimentally because it is a multi-step reaction. Okay, the second thing which I want to tell you is that if you think about the A to D reaction, and if someone asks you that what is the molecularity, you will say it cannot be defined. It cannot be defined, because molecularity actually tells you the number of reactants taking part. And here, my dear students, from the complex reaction, you cannot tell that how many reactants are taking part, because it is involved in different steps. Okay, so this is the first thing which you need to know. I'll make you write this also. Now I want to tell you how can you check that whether a reaction is a multi-step reaction or not from the energy profile diagram. See now, if I talk about the reactants, my dear students, I can say that my first reactant is A, and obviously it has a very high energy. Now A is getting converted into B, so definitely A's energy is comparatively more as compared to B, right? Yes, I hope you're clear with this. That is the reason A is getting converted into B, right? Yes. So from A, let's say this is the energy of B. Now, if you see B is getting converted into C, this means that the energy of B is more than C, and that is the reason B wants to get converted into C, right? Yes. So this means that, let's say this is the energy of C, and now C is getting converted into D, then there definitely D's energy is lesser than C, right? Now let's try to consider each step as a very different reaction. So if I talk about A to B, can I say that the energy profile would be something like this, right? Yes. If I talk about B to C, can I say this will be something like this? And if I talk about C to D, can I say that this would be something like this? Right? Yes. And if we see here, my dear students, this is your transition state 1, this will be your transition state 2, and this will be your transition state 3. So in a multi-step reaction, you have different transition states, right? Yes. This means that here the transition states are more than one, and this is the reason it is a multi-step reaction. When a reaction involves more than one transition state, definitely it is a multi-step reaction, right? Yes. So this is how you understand that how the energy profile diagram tells you everything. Now A has more energy as compared to D, and you can see that how the reaction takes place. Okay, this was the main idea about the multi-step reaction. Okay, and now my dear students, let's write some notes. In multi-step reaction, molecularity has no meaning. So it cannot be defined. Okay. And in multi-step reactions, my dear students, order is calculated experimentally. It can be negative, positive, or fraction. Okay. But if I talk about the single step reaction, I can say that since order is equal to molecularity, and molecularity cannot be negative, it cannot be a fraction, so order cannot be a fraction or negative value. Okay, this is the thing which is important here to note. I hope you have understood this. You can just write this and then we'll move forward. Written? Let's move forward. Okay. Now, let's read the points. Transition state, the state when the bond fission and bond formation, fission is breaking of the bond, formation is the forming of the bond, are simultaneous. Okay. A reaction in which there is only one transition state is known as a elementary process or a one-step reaction. I told you this. If you want to write it, pause the video, write it, and then we'll move forward. Okay. Molecularity is a theoretical concept. Again, my dear students, it is a theoretical concept. It is the number of molecules taking part in one step of a chemical reaction, right? Yes. Next, it is the number of molecules colliding simultaneously in one step of the chemical reaction. Let's say you have two reactants getting, let's say you have A and B, right? This means that you have A and you have B. They both collide. This would be your transition state, right? And then you will get your final product as A, B. So here, my dear students, since it is a single step, the molecularity would be 2. Okay, so the number of reactants actually colliding gives you the molecularity. So pause the video, write it, and then we'll move forward. Okay. Now, since the probability of simultaneous, now my dear students, since molecularity is the number of reactants being collided, this means that maximum of 3 molecules can collide at the same time. Let's say A, B, C. This is touching each other. All of them are touching each other. So the molecularity maximum could be equal to 3. If you take 4 reactants, my dear students, A, B, C and D. This will touch, this and this. But let's say A and D, they are not touching each other. C and B, they are not touching each other. So molecularity cannot be more than 3. It is not possible. Okay. So since the probability of simultaneous collision of more than 3 molecules is very rare, molecularity doesn't exceed the value of 3. Molecularity is always a positive integer. Okay, pause the video, write it, and then we'll move forward. Next, my dear students, molecularity is gettable from the stoichiometric coefficients. I told you molecularity will be equal to the sum of the stoichiometric coefficients of the reactants taking part. And then to get the molecularity, we must take the smallest integer. We discussed about this point in the previous class. So you just need to go through those points and you will be very clear with this particular part. Okay, yes. So pause the video, write these points. We have discussed these and then we'll move forward. Can I move forward? Yeah. Next. Now, for elementary step, that is a single step, order and molecularity are numerically same. I told you that for single step reaction, we can say order and molecularity are same. Right? Order for a one step reaction cannot be fraction. I hope you're clear then, since molecularity and order will be equal. So order cannot be a fraction, it cannot be a negative value. Okay? Yes. Pause the video, write it, and then we'll move forward. Now, let's talk about the multi-step reaction. Now, let's talk about the multi-step reaction. A multi-step reaction is the assembly of many one-step reactions. There are assembly of one-step reactions together combined give you a multi-step reaction. Clear? Absolutely clear. No doubt to that. Next, the slowest step in the multi-step reaction is the rate determining step. Now, this is the important thing which you need to understand. Why in a multi-step reaction, the slowest step is the rate determining step. Now, just imagine you are talking about a marathon where a team of 3 players are actually taking part. Okay. Now, let's take example of Usain Bolt. Let's take Milkha Singh, and let's take Anushka ma'am. Right? Yes. Now, this is a team for the marathon where they have to hand over the what we say that mashal types. I don't know what we call them. A player just runs 1/3 of the ground and then hands over the mashal to the other player, and the other player then covers the 1/3 of the part, and then the other and hands over the mashal to the other player, and then he finishes the race. This is the combined team effort to win the race. Right? Yes, this is something like this. I hope you're clear with this. 1/3 part, 1/3 part, and 1/3 part. Right? Yes. So now imagine these two players are great runners. Right? Yes, they'll run so fast that nobody can match them. Okay, so everybody will be like, yes, now definitely their team will win. Yes. Now I am the third player, and when the mashal comes to me, I'll start running. I run so slow that there's no answer to it. Right? Yes, I'll run so slow, my dear students, that we'll obviously be out of the race. What actually happened here is these two ran super fast. They were the fastest. But how does that matter as long as the third person is not fast? Who is actually deciding whether you will win the race or not? Whose speed is deciding? Are these two deciding, or Anushka ma'am is deciding? Obviously, Anushka ma'am is deciding because her speed is slow. So, whenever you talk about a team, whenever you talk about a combined effort, always whether your work will be done or not depends on the person who is the laziest or on the person who is slow. Right? Yes. So, my dear students, that is the reason whenever you have class projects, everyone wants that they take the brightest student. Nobody wants to take the dumbest student of the class. Right? Yes, because they know he'll not do anything and they'll not be able to complete their project. So that is the most important thing, that whenever you talk about a team, whenever you talk about a combined effort, always and always the deciding factor is the slowest step. And same is the case with the reactions. In a multi-step reaction, you have a combination of many steps, right? Yes, 2, 3, 4, 5, 10, be it any number of steps. Who will decide the rate of the final reaction? The slowest step will define the rate of the final reaction. This is something which you need to understand. Okay. Yes. So this is the reason it is said that the slowest step in the multi-step reaction is actually your rate determining step. Okay. And this rate determining step is known as RDS. Don't get confused if you see somewhere RDS. RDS means the rate determining step. I hope you're clear with this. Pause the video, write it, and then we'll move forward. Okay, perfect. Now, my dear students, if you have written it, now we'll move forward and solve few questions. Let's solve question. Now the question is on your screen. You have to try this question. This question I'll do, and the other question I'll give you as your homework. Okay. So how are we going to solve this particular question? See, you are given a particular reaction, right? And the reaction is 2NO plus Cl2 gives you 2NoCl. Your mechanism is given to you, and you are also given that which reaction is your actually slow step. Okay. And this will always be given to you, which of the following reaction will be a slowest step. Now, since this is the slowest step, can I say that this is the rate determining step? Yes, this is your rate determining step. This step will decide the rate of your final product formation. So now, my dear students, what you will do is that since this is the rate determining step, the rate law will be applied to this particular reaction. Okay. So according to the rate law, you can say that rate law will be applied to slowest step. So according to the rate law, R is directly proportional to the, what are the reactants? NO, NoCl2, and then you have NO. If I consider this as a single step reaction, I can say that the order will be 1 1, right? Yes, this is not your final rate law. This is the rate law that you have applied to the single step. Okay. So this will be your rate law. Can I say that R will be equal to K into NoCl2? NO. Now, my dear students, what the problem is that if you see NoCl2, it is here and then it is here. What do I want to say? You have NoCl2 here and you have NoCl2 here. So what actually is happening is that the NoCl2 is getting formed in the first step and it is getting converted, it is used as a reactant in the second step. This means that it is getting formed in the first step and it is getting used in the second step. The compound which gets formed in one step and is getting consumed in the other step, it is actually a intermediate, and an intermediate can never be present in a rate law. This is the rule. In the rate law, you cannot have a intermediate. So we can say that NoCl2, is getting formed in the first step and is consumed in the second step. So it is an intermediate. And an intermediate cannot be present in the final rate law. So now we need to find some solution to it. We know that NOCl is in the rate law, but we don't want it to be in the rate law. So what happens is, if you see the first reaction, my dear students, always and always your first reaction will be a equilibrium reaction. Now since it is a equilibrium reaction, and if you remember a little bit about your equilibrium chapter, you can say that the equilibrium constant is always equal to the concentration of reactants. Let us say you have NOCl2 divided by the concentration of products raised to the power their stoichiometric coefficients divided by the concentration of reactants raised to the power their stoichiometric coefficient, right? So this will be equal to this into here we'll write the reactants. Okay, now from here, my dear students, I can find the value of NOCl2. The NOCl2 will be equal to K equilibrium into NO into Cl2. Let's say this is your first equation, and let's say this is your second equation. So now I have the value of NOCl2. So now I will put 1 in 2. So you will say put 1 in 2. So your rate law will be equal to K into you have K equilibrium into NO into Cl2. So here it will be K equilibrium into NO into Cl2, and then you have here NO. Let's write it a little bit clearer. You will have K into K equilibrium, you will have NO whole square, and you will have Cl2 raised to the power 1. So now, my dear students, see, K is also a constant and K equilibrium is also a constant, equilibrium constant. You have 2 as a constant and you multiply it by 3. 3 is also a constant. The multiplication of both of them will give you a constant value. So let's say the multiplication will give some constants, which is K double dash. So your final rate law will come out to be K double dash into NO 2 and Cl2 1. This is the final rate law. This is the final rate law, and here there is no intermediate present, right? Yes, where, my dear students, K double dash is the final rate constant, right? And order with respect to NO is 2, and my dear students, order with respect to Cl2 is 1, and overall order of reaction is 2 plus 1, which is equal to 3. So this is how you calculate the order, and this is how experimentally the order is calculated. Okay, yes, and it may or may not be equal to the reaction. In this particular reaction it is equal, but if you will check the other question which I am going to give you as a homework, there the order will not be equal to the stoichiometric coefficients. Okay, so this is how we solve the question. I'll just make you understand what we did. We actually saw the mechanism. We saw which of the following was the slowest step. We wrote the rate law according to that. Then we saw that since we have an intermediate in the rate law, which is the product, the compound which gets formed in one reaction and gets consumed in the other, we just try to remove this. So we use the equilibrium reaction above, we use the NOCl2 value, put it into the first, and then we get the final rate law, and this is how we calculate the order with respect to different reactants and also the overall order of the reaction. I hope you're clear. Pause the video, write this, and then we'll move forward. Okay, write this. Now let's see what we have done in this particular question. Everything is written here. Second step itself is the elementary process for which order and molecularity are equal. The intermediate can't be present in the overall rate equation. The rate of the overall reaction is equal to the rate of the rate determining step, but the rate constant of the overall reaction may not be equal to the rate constant of the rate determining step, because if you see final rate constant K double dash was actually equal to K into K equilibrium, right? Yes. For the one-step reaction, the order corresponds to the stoichiometric coefficients. If the order is found to correspond to the stoichiometric coefficient, the reaction may or may not be a one-step reaction. Right? Yes. These are the few points. You can just pause the video, write it. We have discussed everything in detail, so you will not have any issues. I hope you're clear with this. Now let me give you this question as your homework. This will be your homework question. Try the question yourself. I'll make you understand. I'll solve this question in the next class, but this question will be solved exactly like the previous question. First, see the slowest step, write the rate law, find the intermediate, use the equilibrium reaction, put it into this, and then get the final rate law and the final orders of the reaction. Okay, so this will be your homework. So let's try to solve a few questions. The first question is, which of the following statement is incorrect? You have to tell which of the following statement is incorrect. Try it yourself. Pause the video. First try it yourself and then see ma'am's approach. See. Option, we'll start from the last option. Okay. It says that first order reaction may be complex or elementary reaction. It says that if you are given that order of reaction is equal to 1. Since order is equal to 1, it can be a multi-step reaction or it could be a single step reaction. Right? Yes, both are possible if order is given. Yes, ma'am. So a first order reaction may be a complex or elementary reaction. Absolutely right. So first this statement is correct. Let's talk about the other. Zero order reaction must be a complex reaction. See, my dear students, if they are saying zero order reaction, this means that your order is 0. Now if it is a single step reaction, then order should be equal to molecularity, and if order is equal to molecularity, then this means that molecularity will also be equal to 0. But molecularity can never be equal to 0, because molecularity actually tells you that how many reactants are colliding, and here it is telling you 0 molecules are colliding, and if 0 are colliding, then how is the product getting formed? This means that for zero order reaction you cannot define your molecularity, and it will always be a complex reaction. So this is also right statement. Let's talk about this statement. A bimolecular reaction. If it is a bimolecular reaction, means molecularity is 2. If molecularity is 2, this means that it is a single step reaction. Right? Yes, we can find it. Next, must be a second order reaction, and yes, for a single step reaction molecularity is always equal to order, and since the order is 2, it is a second order reaction. So this statement is also right. Now let's talk about the first statement. A second order reaction. Now you are given order equal to 2. This means that it can be a complex reaction or it could be a single step reaction. Both are possible. Okay. It must be a bimolecular reaction. This means that if it is saying that if you have order 2, it should be a bimolecular reaction, means that molecularity should be 2. No, if it is a complex reaction, then you cannot define its molecularity. Right? Yes, this means that this statement is wrong. So option A will be your correct answer. This was a very important question for you to understand. I hope you're clear with this. Pause the video, write it, and then we'll move forward. Let's talk about the other question. The molecularity of a complex reaction given below is, try the question yourself, it is just a 2-second question. It says that you are given a reaction and you have to tell the molecularity. It is given, my dear students, since we see that here it is 2, so can I say the molecularity is 2? If you are saying that yes ma'am, option B is your correct answer, then let me tell you, you're absolutely wrong. Why? Because in the question it is very clearly told you that it is a complex reaction, and since it is a complex reaction, means it is a multi-step reaction, and for multi-step reactions, my dear students, you cannot define the molecularity. So if we cannot define the molecularity, then option D, that molecularity has no meaning, will be your correct answer. I hope you're clear with this. This is how you will be solving these types of questions. Okay, perfect. Pause the video, write it, and then we'll move forward. Okay, I hope you've written this. Now let's move forward, my dear students. Now we will be talking about the zeroth order reaction. Now one by one we will be talking about zero order reaction, first order reaction, because we have to understand them in detail. Okay. So if I talk about a zero order reaction, this means that, ma'am, you, according to the rate law, R is directly proportional to the A raised to the power n, where R is the rate of reaction, A is the concentration of reactant, and n is the order of reaction. Right? Yes. And since it is a zero order reaction, my dear students, can I say that n is equal to 0? First, let's write it. Let's write R is equal to K A raised to the power n. Okay. And I know that since it is a zero order reaction, so this means that n is equal to 0. And if n is equal to 0, then this means that R is equal to K A raised to the power 0. Now, my dear students, anything raised to the power 0 is equal to 1. This is a maths concept. Anything raised to the power 0 is actually equal to 1. So this means that R is equal to K. R is equal to K. So for a zero order reaction, my dear students, rate is always equal to the rate constant. If you want to write it, you can write that K is the rate constant. So for a zero order reaction, my dear students, rate is always equal to the rate constant. Okay. So if you are ever asked to plot a graph between the rate and concentration, for if you are asked to plot a graph between the rate of the reaction and the concentration for a zero order reaction, what will be the plot? Ma'am, it does not depend on the concentration of the reactant. It does not depend on the concentration of reactant. Just see, it doesn't depend. So this is always a constant value. This is always a constant value, right? Yes. So this is something which you need to understand. The plot for a zero order reaction of rate versus concentration will always be constant. Okay. Yes. So now let's talk about the unit. Okay. So unit of rate is always mole liter inverse second inverse. This is always the unit for rate. So let's see that what is the unit of rate constant, because according to this, the unit for rate constant should also be equal to the unit of rate, because if they both are equal, then they both should have the same units. Now let's see, using the general formula we calculated in the first lecture. I hope all of you remember the general formula. The general formula was mole 1 minus n liter n minus 1 second inverse, right? Since it is a zero order reaction, so I know that n is equal to 0. So the unit would be mole 1 minus 0 liter 0 minus 1 second inverse. So the unit of rate constant is mole liter inverse second inverse, which is exactly equal to the rate of the unit of the rate. This means that whatever we have done till now is absolutely right. Right? Perfect, my dear students. I hope you are clear with this concept. What we did right now, we plotted a graph, we actually cross-checked our answer, and also we came to know that for a zero order reaction, the rate of the reaction does not depend on the concentration. If you want to write it, you can write this point also. For zero order reaction, rate of reaction does not depend on concentration of reactant. Okay. Perfect, my dear students. Just pause the video, write it, and then we'll move forward. You can write this. Okay, let's move forward. See, The unit of rate constant provides the overall order of the reaction. If you were given the rate constant, you can just check the rate constant's unit and see that which order of the reaction are they talking about. Next, the rate law provides the variation in rate with concentration. Okay, so if you see the rate law for zero order reaction, you know that R is equal to K, so it is independent of the concentration of the reactant. In zeroth order reaction, the rate is independent of the concentration and remains constant throughout the reaction. Clear? Yes, I hope you're clear with this. Now my dear students, we will be calculating, just a second. Yeah, it is clear, it is clear. We'll talk about all this now. We will be writing the integrated rate law for the zeroth order reaction. How are we going to do that? Let's see. You can write the heading as integrated rate law for a zero order reaction. It is clear since we are talking about the zero order reaction. So integrated rate law, my dear students, the reaction is, let's say the zero order reaction is from A to B. So we know for a reaction, how do we write the rate? How can we write the rate? Let's see, my dear students. Just try to write both of the rates and then we'll move forward. Okay. So for integrated rate law, how can we do this? Okay, so now imagine, my dear students, I have told you that how to calculate the rate. You can calculate rate in two different types, right? We know that we can calculate rate, that is the instantaneous rate, as minus of dA by dt. We can calculate it like this. Yes, this is the first type of rate we started learning how to write the rate. This was the first type. Yes, and the second was the rate law. And according to the rate law, we can say that rate is directly proportional to A raised to the power n. Now since n is your order and order is 0, so we can say that rate is equal to K into A raised to the power 0, and rate will be actually equal to K into 1. So rate is equal to constant K, right? Yes, this is your second type of rate, right? Yes. So we actually calculated the rate in two different forms. The first was the instantaneous rate and the other was from the rate law. Since we are talking about the same reaction, this means that since we are talking about the same reaction, we can say that both the rates should be equal to both the rates should be equal. Yes, ma'am, we can say, obviously, since we are talking about the same reaction, the rate will be equal. So I can say that 1 is actually equal to 2. Yes, so let's equate both of them. Minus dA by dt will be equal to K constant. Okay, perfect. I hope there is no issue till now. Now let's just cross multiply it and convert it into a bit beautiful form, right? Yes, so let's say that I said minus dA is equal to K dt. I can also say that dA will be equal to minus of K dt, right? Yes, we just cross multiplied it. We haven't done anything till now. Okay, till now everything was good, everything was beautiful. What will happen now is, my dear students, that we will do something which you will never like, that is integration, right? Yes, but don't worry, I am here. I'll tell you every step what am I doing with the integration. Okay, so now we will be integrating on both sides. So integrating on both sides. So let's just integrate it. This would be integration of dA. Let me write it with a different color. Let's write with dA will be equal to integration of minus K dt. Now since K is a constant, it cannot be integrated, it will come out. So integration of dA will be equal to minus K integration of dt. Okay, I hope you're clear with this. Now I am going to tell you a few integration formulas which we will be using here. So now, my dear students, when we integrate anything dx, we get the integration as x. Whenever we integrate anything dx, we get the integration equal to x. Okay, so if I am using this to this expression, I am using this expression, okay, to integration of dA is equal to minus k integration of dt. So I am using this, my dear students. Can I say that this is equal to a, because dx integration is x, so dA integration would be a from a naught to at. I'll just tell you what are these. Then minus k, you will not integrate k, but you will integrate t, so t will be from 0 to t. Now let's see what these symbols denote. Okay, so a naught is the concentration of reactant at t is equal to 0, and at is the concentration of reactant at t time, at some t time. Okay, so whenever you integrate and put the limits, let me just write the limits also, from a naught to a t, from 0 to t. This was the integration that we were doing, and these were the limits. Initial integration to some t time integration. Now see, whenever you put the limits, the upper limit would always be put first and then minus the second limit. Okay, so this would be at minus a naught. This will be equal to minus t minus 0. This is something that we came out with. So we can say that at minus a naught is equal to minus kt. So at is actually equal to a naught minus kt, and this is your final integrated rate law for zero order reaction. This is something which you need to remember. So this is the integrated rate law for zero order reaction, and this will be used in n number of formulas. Okay, so I hope you are clear how to calculate the integrated rate law. So this is how we will be calculating the integrated rate law. So you can pause the video, write it, because we will be using this again and again. You know what is AT? Concentration of reactant at T time. A naught initial concentration, K is the rate constant, and T is the time taken. Okay, so pause the video, write it, and then we'll move forward. I hope you've written it. Pause the video, write this as well. Okay, I hope you have written this. Now my dear students, we will be plotting a plot. Okay, so let's write the integrated rate law. What is the integrated rate law? AT is equal to A naught minus KT. Let's write a straight line equation. Y is equal to C plus mx. So can I say that my y-axis is actually AT, my x-axis is actually time t, and my intercept C is A naught, and slope m, which is also equal to tan theta, is minus 1, minus k. It is minus k. So now let's try to plot the graph. If I plot a graph, it will be a straight line with a negative slope. It will be a straight line with a negative slope. Y-axis is AT, the concentration of the reactant at T time. This would be time T, and it will be a negative slope straight line. And my dear students, this intercept would be your A naught, and your slope is m, which is equal to minus of k. So this is how you will be plotting the graph. It is a straight line with a negative slope. I hope you're clear with this. Perfect, my dear students. You can pause the video, write it, and then we'll move forward. I hope you've written it. See, Now, since rate is not defined as zero concentration of reactants, the horizontal line must not be in contact with y-axis. So now, my dear students, what it is telling us that the plot which we initially plotted between the rate and concentration of the reactant, it said that it should be a straight line and it should not touch it here. It should not touch it here, because this means that you don't have the concentration of reactant, and if you don't have the concentration of reactant, that means there is no use of the reaction, right? Yes, so this should not touch, this will be a little bit away. This is something which is told you here. You can pause the video, write it, and then we'll move forward. Next, in a zeroth order reaction, the concentration decreases linearly with time. I hope you're clear with this. We just plotted the graph that the concentration of reactant with time, the plot is linearly decreasing, right? Yes. So this is what they are telling you here. The unit of rate constant must remain the same in the rate law and integrated rate law. Yes, because rate constant is rate constant, its unit will never change. Clear? Pause the video, write all the points, okay? Okay. Now, my dear students, we will be calculating the half-life and half-life period. What is half-life? So, you have some initial reactant, you have some initial concentration of the reactant. The reaction it took place, and there was a time where half of your reactant was consumed. So, how much amount of your reactant is left now? Half of the initial amount, and this particular time is actually known as the half-life of your reaction. So what is half-life? The time, half-life is the time at which half of your reactant has been consumed. Half-life is the time at which half of your reactant has been consumed. Okay. I hope first you want to write the definition, so just write the definition. The time required for the concentration of the reactant to become half of the initial value is known as the half-life of the reaction. If you have initial concentration A naught, then at half-life, my dear students, your concentration T, this will become A naught by 2. Where? At half-life. Okay? At half-life, my dear students, the concentration of the reactant will become half of the initial amount. Perfect. I hope you're clear with this. Now we'll understand the half-life. And how can we understand? It is very, very easy. You just have to write the integrated rate law and you can calculate anything. Okay. So first we'll write the integrated rate law. Integrated rate law. What does the integrated rate law tell you, my dear students? It says that A T is actually equal to A naught minus K T. Okay, so this was the integrated rate law which is applicable everywhere. Now, at half-life, if I talk about half-life, can I say that my time will be equal to T half? I can say that T will be equal to T half because T half denotes the half-life. Okay, and the concentration of my reactant at half-life will become half of initial amount. It will become A naught by 2. I hope you're clear with this. Yes, perfect. So now let's just put these values into this. This would be A naught by 2 minus is equal to A naught minus K T half. Okay, so let's subtract this. K T half will be equal to A naught minus A naught by 2. So K T half will be equal to A naught by 2. Right, and from here you can say that your T half will be equal to A naught by 2K. This is the final expression for half-life. Just a second, my dear students. Okay, so due to some technical issues, I'll have to start from here again. So just let's revise, right? We'll revise it and you will be clear with this. See, if your T is equal to T half and A concentration at at the half-life would be equal to A naught by 2, let's just put it into this. A naught by 2 will be equal to A naught minus K T half, right? Yes. So your KT half will be equal to A naught minus A naught by 2. So T half, KT half will be equal to A naught by 2. And from here we can say that T half will be equal to A naught by 2k. This is the expression which you need to understand. It is very important that the half-life expression is this, and you will be asked numerical, so you need to memorize this expression. The half-life expression is A naught by 2k, that is the initial concentration of the reactant to the initial concentration of the reactant divided by 2k. Okay. So now, my dear students, this is how we plot the graph for half life. Sorry, not graph. This is how we find out the expression for half life. Okay. Yes. I hope you are clear till now. First write it and then we'll move forward. I hope you've written it. Now, my dear students, what we will be understanding from here is that you know that K is a rate constant, it will be a constant value. So, can I say that half-life of a zero order reaction is directly proportional to the concentration of the reactant. It is directly proportional to the concentration of the reactant, right? Yes. So, this is something which we will be using while plotting the graphs. Okay. So what I want to tell you, the most important thing here is that, my dear students, just imagine, I hope you've written this. Now see, imagine you had some 50 amount of your reactant and then it got consumed and you got 25 amount and then it got consumed I am actually calculating the half life. So from 50 it came out to be 25, then 12.5, and then, my dear students, 6.25, and so on. Okay, so this is something how we are talking. So you had initial amount of 50 amount of reactant, it got half, so this is a half life. Okay, this will also be a half life and this will also be a half life. Okay, yes. So what actually tells us that if it is a zero order reaction, my dear students, then for a zero order reaction, if your this half life is, let us say, 10 minutes, okay, then the half life, the second half life, will definitely be less than 10 minutes. Why? Because half life depends on the initial concentration of the reactant, and if the initial concentration is more, the half life will be more. Since the initial concentration is less, the half life will be less, let's say 5 minutes. If the initial concentration is more or less, then this will be, let's say, 2.5 minutes. So this is how we say that the concentration of the reactant actually decides the half-life. The more the concentration, the more will be the half-life. The lesser the concentration, the lesser will be the half-life. For a zero order reaction, this is something to understand. I hope you're clear till now. Now, my dear students, now we will be plotting a graph. Do we have an option of plotting a graph here? Okay. No. Let's draw a graph on our own only. Okay. So now, my dear students, when we will plot a graph, we know that T half, let me write the heading as graph. We know that T half is equal to A naught by 2k. Okay. So if I plot a graph, can I say that y is equal to mx, a straight line equation, where, my dear students, your y-axis is T half, your x-axis is A naught, and your slope m is 1 by 2k, right? Yes. So what will be your plot? You will just draw a plot. Your y-axis is T half, your x-axis is A naught, or you could say concentration of the reactant, and your slope is positive, so this will be something like this. But when you study this, you will study like, as the concentration is, you will be studying it like this, because the concentration of your reactant will keep on decreasing, so your half life will also keep on decreasing. Okay, so the plot will be something like this. The plot between T half and the concentration of the reactant will be like this. Okay, I hope you're clear with this. These were the few things which you need to know about the zero order reaction. Only then you will be able to solve the questions. Okay, yes, perfect, my dear students. Pause the video, write it, and then we'll move forward. I hope you've written it. Now, let's move forward. Now, let's talk about a few examples in our day-to-day life where zero order reaction takes place. So most of the heterogeneous catalytic reactions are zeroth order reaction. You might have studied, my dear students, in organic that CH2 can be converted into CH3. That is, you can hydrogenate it. Hydrogenation of an alkene, it happens in the presence of, like, let's say nickel. This is an example of, you have H2, you have nickel, right? So the hydrogenation examples are for a zero order reaction. All these reactions are actually zero order reactions. The other example is most of the photochemical reactions. You might have studied that you have a alkane and you react it with H nu, you have, let's say, Cl2, then you get something like Cl here or Cl here, right? Yes, so these are your catalytic reactions, my dear students, and these all photochemical catalytic reactions are actually your zero order reaction. Okay, yes, I hope you're clear with this. Perfect, my dear students. You can pause and write it. Sometimes questions are asked from this particular part as well. Okay, perfect. Now, let's see. Calculate the time needed for the 70% completion of a zeroth order reaction. T half is given as 30 minutes. How will we be solving such types of questions? Let's see this, my dear students. We know that the integrated, for these types of questions, you only need to know the integrated rate law. The integrated rate law is for zero order reaction that A of T is equal to A naught minus K T. Okay, yes, and I am given the half life T half equal to how much? 30 minutes. Okay, what is the role of 30 minutes? Let's see. We know that, my dear students, T half is actually equal to A naught by 2K. So can I say that rate constant K will be equal to A naught by 2T half? Right? Yes, perfect. So this will be equal to A naught by 2 into, what is the value for T half? 30. So this is something we have calculated the rate constant as this. Okay, yes. So this is the rate constant. This was the main purpose to give you the half-life. Okay, so now you're given that 70% of the reaction is completed. Let us say your initial amount of reactant is A naught. It is the initial concentration. After, my dear students, 70% completion, what will be 80? 80 is the concentration of the reactant left. Okay, now since 70% of your reactant is consumed, so initially you had A naught, and out of this 70 upon 100 of A naught is consumed. So this will be equal to your 80. I hope you're clear. 80 is the concentration of the reactant left. If you had initially A naught reactant and 70% of it is consumed, then how much is left? A naught minus 70 upon 100 of A naught. This will be the value for 80. So let's calculate it. This will be 30 A naught upon 100. Now you have this value, you know this, you know this. Can you calculate T? Yes, just put the values here. What is 80? 30 upon 100 of A naught. So 30 upon 100 of A naught will be equal to, you have A naught again, so here will be A naught minus, you just calculated the value of A naught by 60. This would be A naught by 60 into T. T is something which you have to calculate. Okay, so we can cancel A naught. This would be 3 upon 10 is equal to 1 minus A naught upon 60 into T. So let's just bring it here and take this that side. So this would be A naught by 60T will be equal to 1 minus 3 upon 10. So A naught, why am I putting A naught, my dear students? A naught is cancelled, right? It is cancelled. This is 1 upon 60. I am sorry. Or we could say that this is T upon 60, right? Okay. So now let's solve this. T upon 60 will be equal to 1 minus 3 upon 10, right? Yes. So T upon 60 will be equal to 10 minus 3 is 7 by 10. This would be cancelled. So T would be 7 into 6. This would be 7 into 6. I hope you're clear till now. This time would be 42 minutes. 42 minutes. So the time required for 70% completion of the reaction is 42 minutes. This is how you will be using your integrated rate law for that particular order of the reaction and calculate the whatever is asked to you. But you need to understand each and every concept to apply in these types of questions. I hope you're clear with this. You can pause the video, write it. You can write this. Perfect. With this, my dear students, let's end our session today. We will be covering the first order reaction in the next session. For that, I want you to try to understand the first order from the NCERT part. If you are not able to understand, don't worry, I am here. Why to fear? Right? Yes. Keep revising, keep practicing. You are getting your practice sheet. You have to practice questions. Only then you can excel in physical chemistry. Let's meet in the next lecture. Keep on studying. All the very best. Thank you so much.